And again, the reason why I don't want to worry about cotangent because it just gets to be way too messy with the asymptotes. So when we're dealt with reciprocal functions, remember we kind of alluded to this a little while ago. If I look at secant, secant is the reciprocal of what? Cosine. Cosecant's the reciprocal of sine. All right. So when we did cosine graphs, and this will be really, really straightforward here. When we do a reciprocal graph, what we do is we start by plotting the normal functions graph. So if I look at a generic cosine graph, where does cosine start? At A. So if I'm going to graph y equals cosine of x, for example, what's my A value going to be? 1. Good. So I'm going to plot this at going from 1s to negative 1s. When you have that generic, we did the very first day of graphing these things last Thursday, we said that cosine as well as sine has a period of what? Yeah, 2 pi. Just generically, it's a 2 pi. So it'll be 2 pi over b. In this case, our b value is 1. So we know we have a 2 pi out here. So what we did was we took the 2 pi, we cut it in half again, and put it back to here. And we know that this was at 0. So far, so good. Then we also learned that how we graphed cosine is that cosine always started at its A value, went to 0, opposite of A, 0, back to A. So the generic version of cosine was this. And we got this graph. We okay with that? That's what our first function of cosine looked like. Now, when you look at it in terms of a reciprocal, when you reciprocal stuff, you flip the fraction. You're okay with that? And that's what we're doing with secants, and that's what we'll do here in a little while with cosecants. So what I want to think about is, when you're looking at the reciprocal form of this, I'm going to graph that in blue. What's the reciprocal of 1? 1. Okay. What's the reciprocal of 0? Very good. So what happens at the 0 then? An asymptote. Excellent. What happens at, what's the reciprocal of negative 1? Negative 1. You're just flipping the fraction. What's the reciprocal of 0? Asymptote, yeah. Undefined, very good. And then again, what's the reciprocal of 1? So right now, all I have are these 3 points and 2 asymptotes, but I have no idea what the rest of the graph is doing. So we have to do a little bit of thinking. Do you guys agree that somewhere about here is negative 1/2? Do you also agree that somewhere about here is positive 1/2? So if this line happened to be this dot, oops, let me make that red. If this dot was 1/2 on the cosine graph, where would it be on the secant graph? Excellent. The reciprocal of 1/2 is 2. So that means that somewhere up here, when I reciprocal this, it goes to 2. Oh. What happens when it's at negative 1/2? It becomes negative 2. Which means it's here again. And here, there's a 1/2 somewhere here. So what happens here with cosecant, with secant graph, and cosecant here in a little while, is that it takes the sine or the cosine graph and basically blows it up. Okay? You get curves that look like this. The blue line becomes the generic graph of a secant trig function. all we did is we took the reciprocals of generic points that we know. Right? Generic points that we know. You can also go through, if you want to think about it, at 1/3. You know, that somewhere along that curve, you're going to get cosine of 1/3. Well, that means that the secant would be up at 3. So you get stuff like that. All right. That's what the generic secant looks like. When I do cosecant, it's very similar to it, but it just gets shifted a little bit. I don't know if you noticed this, but sine and cosine graphs, they're only shifted pi/2 from one another. Let's look at cosine. If I want to do, we'll graph a sine in blue, like we would normally. We'll do the same thing. Let's go 1, -1. Your generic sine graph, your parent function, where does sine always start?
At 0.
It starts at 0. Okay. It starts at 0, then it goes to the a value. If it was positive, it goes up. If it's negative, it goes down. These same rules are going to apply as we get going into the reciprocal. Because what we're going to do is we're still going to graph our standard function and then blow it up. It's very, very simple to do. Now we've got 5 points, don't we? All right? Change our color. What's the reciprocal at 0?
I have no.
So I know I have 3 asymptotes now. Yes, sir. What's the reciprocal of 0? That's hard. Remember, at 0, that means this fraction is 0/1. When you flip it, you get 1/0, which is undefined. What's the reciprocal of 1? 1. Reciprocal of -1? Somewhere in between here and here is halfway, which means there's halves. There's a half here, there's a half here. There's a negative half and there's a negative half, which means there has to be a 2. And you get those graphs. Do you see what I'm kind of saying by we're just blowing them up? Instead of being the curve, the peak becomes the valley. The valley becomes the peak. Because they're inverses of one another. It has its ups and downs. Yeah, I got you to laugh. That's good. That means a lot to me. Yes, hi for you.
So you look at the y
Yeah, we're looking at this ordered pair. We know that this is 1. What's the reciprocal of 1? It's 1. Reciprocal of 1/2 is 2. Yeah, that's all we're doing. That's all we're doing here. All right. All right. Now, the weird stuff starts to come into play when we have the shift to these. Now, as you guys saw yesterday, the way that we shift things, it takes a little bit of time. You go through some ordered pairs, you plot stuff and go. You have to readjust and do all these things. With reciprocal functions, what I'm going to do is I'm going to give you guys a different way to set it up. For example, let's do this. Yesterday, what would you do right away with those values in the parentheses? You would take the 4 out. Okay? Today, when we see the value stuck within the parentheses, I'm going to show you guys a different way to graph these. And this is we're only going to graph it this way for reciprocals because it still takes a little bit of time, but it's cleaner as opposed to trying to go through the whole rigmarole of all the other nasty stuff. Okay. So what we do here is this. There's this nice little shortcut for reciprocals. This is written in this format that's called bx plus c. All right. When you have a reciprocal trig function, and like I said, it's only going to be cosecant or secant. It will be written in this format. There's a shortcut to figure out your period and your breakpoints. What we do is we take this value, set it equal to 0, and we take that value and set it equal to 2 pi. Because doesn't sine and cosine start at 0 and end at 2 pi? By figuring out what's in the parentheses, the values of x that'll generate your start and your finish for your period. It's a nice shortcut that works very well for cosecant and secant. Okay? Works really, really well for this setup. So now I just solve the equations. Hopefully we can get x by itself rather quickly. I get pi over 4. Right like that. And the other one we get 3 pi over 4. Yes. But the k value, we're just going to move it vertically. It's not going to change it. The period won't change because the vertical to it. It's still going to be this set, so it's just going to move up or down. All right, good question. Yes, sir?
So when you're using the bx plus c, you're going to set it equal to 0, and then also your period.
0 and 2 pi every time.
All right, 0 and 2 pi every time?
Yep. That'll give you your starting spot of the period and your ending spot for the graph. Because we're only going to graph one thing. All right. So I know that it's going to start at pi over 4, and it's going to end at 3 pi over 4. What's halfway between pi over 4 and 3 pi over 4? Pi over 2, good. This is where we have to figure out some other fractions. What's halfway between pi over 4 and pi over 2? Well,
Wait, 2. Wait.
All right, so think of it this way. What we're doing here is we're finding the midpoint, we're finding the average. What's 1/4 plus 1/2? 3/4. What's half of 3/4? 3/8. So it's 3 pi over 8. Okay.
Oh, I didn't know.
You're not stupid, you just forgot how to do fractions. This is the weird fraction stuff. But again, they're not tough once you remember how it goes. Okay? So now you've got this middle point here, you're like, oh yeah, I'm an idiot. Oh, 2/8, 3/8, 4/8, 5/8. Okay? Now, in this problem, this was a cosecant, if I'm not mistaken, correct? Okay. This cosecant problem, what was its a value? 1. So when I do the sine graph to start, what's the amplitude of my sine graph going to be? 1. So I know that I'm going to generically start this. It's going to go to 1, -1. Now, I'm only looking at this graph now as it's shifted, but I'm going to plot the sine graph first. Okay? My sine graph, it always starts where? At 0. So in this case, the 0 spot starts at pi over 4. Right? Because we've already pre-shifted it the shift. Okay? We've pre-shifted this. Then it goes to here. Oop. Yes, ma'am.
So
Yep, that's your left boundary or right boundary. These things. Okay. Now I know from here, I've already shifted everything. My A values are set because it's just ones. Now I just have to reciprocal everything. I've got 5 points to reciprocal. What's the reciprocal of 0? Asymptote. 1. Asymptote. -1. Asymptote. Somewhere in between here and somewhere in between there, there's a half, which means there's going to be a 2. The trick for writing these out is it's really tough to do your ordered pairs on these because you have to figure out what values at the halfway between the 4th and the 3/8. It just starts to get way too messy. So what I'm going to ask that you guys do for writing some ordered pairs for these is that I'll ask you to write out the ordered pairs of the parent, like whatever the sign was, with its new period. Does that make sense? So my ordered pairs I would write down would have been pi over 4, 0. 3 pi over 8, 1, and so on. But then you would draw in your asymptotes and your 2 blow-ups or whatever you have to do. Okay, does that make sense? Go ahead. No, I would ask you to list the other ones through, and we'll do. I wanted to just show a generic idea here. And the next one I do, I'll write out how I would. Okay. Yes, ma'am.
So with that same equals 0, you say that's for both or just because?
What do you mean?
Like, you're saying it equals 0, it's like sine
It still starts at 0, but when it's at 0, it starts at 1. So if this was a secant graph, then this would have been at 1 and would have moved itself around and done other things. So, but for what we're looking at here, that's what we're going to start with. But yeah, cosecant and secant, figure out that bx plus c jump, 0, pi over 2, or sorry, 2 pi. All right, let's try to. Let's see, we did this. Cosecant, let's do a secant. Secant is the reciprocal function of cosine, very good. So we know that first thing we'll do is do our 2x minus pi equal to 0, and 2x minus pi equals 2 pi. So add pi divided by 2, my left boundary becomes pi over 2. Add pi divided by 2, my right boundary would be at 3 pi over 2. Are we okay with that? The amplitude of the cosine graph we're going to do is going to be 2. So the A value is 2. What's halfway between pi over 2 and 3 pi over 2? Pi. What's halfway between pi over 2 and pi? There you go. So if you start thinking about it in terms of, like I always was saying, look at that that second fraction we always do. It's a fourth, so 2/4, 3/4, 4/4, 5/4. Cosine, does it start at 0 or start at its a value? In this case, a value is 2. My ordered pairs, this is what I would write here. I would have, I know I'm at pi over 2, 2, 3 pi over 4, 0, pi, negative 2, 5 pi over 4, 0, 3 pi over 2, back to 2. Those are the ordered pairs that I know I can list without too much of a hassle. What's the reciprocal of 2? Oh, but, all right. So if I did the 1/2 here, wouldn't it drop? So the idea here is the a value always stays. The a value is going to be the same. This is now technically your 1. This is technically your negative 1. The halfway point is going to be in here, and that's what blows it up. So your a value stays. The peak of your a value for the cosine becomes the valley of your secant. Your a values will always be the same when they flip. All right? Whether it's sine or cosine, that a value, the amplitude is going to be the bottom of a cosecant or a secant graph, or the top of the sine or the cosine graph. Your asymptote is here. Your asymptote is here. So it's going to go what'll happen is, if your a value is 2, when you blow it up, the next one will be at 4. The a value is at the negative 2, when you blow it up, it'll be down at negative. Yes, ma'am? Yes. Yep. Remember that there's these 2 points here and here. So it's just a reciprocal of whatever your a, you double the a values you put down. It's like a multiplier. Yeah, it's in, yes. What do you mean? Yeah. Okay. So think of it as, let me move this out of the way. Let's say this is at 1. What's the reciprocal of 1? 1. Do you agree then halfway between 1 and 0 is a half? So what's the reciprocal of a half? It doubles. Okay. Now, since this is at a 2, it's always going to be the bottom of the reciprocal function. In this case, this is the bottom of a secant. Since it's at 2, the reciprocal, the halfway point, if you will, is still would be at 1, but you've got to double it as you blow it up. You're doubling it off of here. All I need you to remember is that how do you set up those two? Get your points, knowing that if this is at 2, this next one is double. If this is at 3, what do you think this would be at? There you go. It's that straightforward. If it's at negative 2, it's going to end up being at beta 4. That's it. It's nothing, because getting those actual ordered pairs is pretty tough. I just want you guys to get the generic shape. If you can give me asymptotes and get that truncated way of doing the period, I'm cool with it. The rest of it just becomes gravy. That's something Miss Denny will show you. All right? But I left your homework in my office. I'm so excited to do something. I'll be right back. I got 4. That was a shot. We'll see how we do.